In the early years of World War II, American military planners watched the skies over Europe with growing unease. Reports coming out of Poland, France, and later Britain painted a troubling picture. German fighter aircraft were fast, agile, and terrifyingly effective. The Messerschmitt Bf 109, in particular, had proven itself capable of climbing higher and striking faster than most Allied fighters. For the United States, still not fully engaged in the war, this was more than a warning, it was a challenge. American aviation doctrine before the war placed great faith in industrial power and long-range bombing. The belief was simple: mass production and technological innovation would eventually overwhelm any opponent. But German successes forced U.S. engineers and strategists to confront an uncomfortable truth. In the thin air above 25,000 feet, Luftwaffe fighters could intercept bombers with relative ease, while American aircraft struggled to match their performance. As intelligence reports circulated through the Army Air Corps, urgency replaced confidence. If German fighters could dominate high altitudes, then the U.S. needed aircraft that could fly higher, faster, and longer. Engineers were told to push designs to the edge of what was physically possible. New engines were tested for extreme altitudes. Turbo-superchargers were refined. Experimental aircraft were proposed that promised breathtaking ceiling limits, on paper. But this race was not only about machines. It was driven by pride and fear. The idea that German engineering might permanently outclass American aviation was unacceptable in Washington. Every technical briefing carried the same unspoken message: the United States could not afford to lose control of the sky. What few planners fully understood at the time was that altitude came at a hidden cost. As designs chased German performance figures, human limitations were quietly pushed aside. By 1940, the reputation of German fighter aircraft had become a serious concern inside American intelligence circles. Combat reports from Europe consistently pointed to two machines that seemed to define Luftwaffe air superiority: the Messerschmitt Bf 109 and the Focke-Wulf FW-190. To U.S. analysts reading intercepted reports and pilot debriefings, these aircraft were not just effective, they were alarming. The Bf-109 had already proven itself during the invasions of Poland and France and later in the Battle of Britain. Its greatest strength was speed combined with an exceptional rate of climb. German pilots could engage on their own terms, attacking from above and disengaging almost at will. For American planners, this ability to dominate altitude was deeply troubling. High ground in the air meant control of the fight, and the Bf-109 usually had it. Even more unsettling was what followed. In 1941, intelligence began circulating about a new German fighter that British pilots described as shockingly fast and brutally efficient: the Focke-Wulf FW-190. Early encounters revealed an aircraft that outperformed many Allied fighters in roll rate, acceleration, and low to mid-altitude speed. RAF pilots were stunned. Some initially believed they were facing an entirely new class of aircraft. Altitude performance was only part of the problem. German fighters were engineered with combat efficiency in mind. Armament was heavy, cockpits were compact, and visibility during attack runs was excellent. These design choices reflected Germany's focus on short, violent engagements rather than long escort missions. In these sudden encounters, German pilots often struck first and survived. American observers took careful note. The concern was not merely that German fighters were fast, but that they had been designed around real combat experience. Luftwaffe pilots had been fighting continuously since 1939, refining tactics while the United States remained officially neutral. Faced with the growing dominance of German fighters, American air planners reached a bold and risky conclusion: if the Luftwaffe controlled the lower and mid-altitudes, the United States would go higher. In Washington and at aircraft factories across the country, a new concept began to take shape, one that treated extreme altitude not as a limitation, but as a weapon. The logic seemed sound. At heights above 30,000 feet, the air thinned, engines struggled, and human endurance faltered. German fighters, optimized for European battle conditions, were believed to lose much of their advantage in this hostile environment. If American aircraft could operate reliably at such altitudes, they might strike targets while remaining beyond effective interception. On paper, it was a brilliant way to bypass the Luftwaffe rather than confront it head-on. This idea quickly reshaped U.S. aircraft development. Engineers were instructed to design fighters and bombers capable of sustained flight far above existing combat ceilings. Turbosuperchargers became essential. Wing designs were altered for thin air performance. New oxygen systems were rushed into production. Experimental projects promised ceiling limits that had once belonged only to record-breaking test flights. The U.S. Army Air Forces placed enormous faith in engineering solutions. Problems of cold, oxygen deprivation, and pilot fatigue were acknowledged, but often minimized. Military reports assumed that improved equipment, heavier clothing, and better training would solve these issues over time. The immediate priority was reaching the altitude advantage before Germany could adapt. Test flights soon began pushing pilots into an environment few humans had ever experienced for extended periods. Temperatures dropped to deadly levels. Frost formed inside cockpits. Controls stiffened, and simple movements became exhausting. Yet the data gathered from these flights fueled optimism. As American aircraft climbed higher and faster, a dangerous imbalance began to emerge. Engineering progress surged ahead, but the human body remained unchanged. In the race to outperform German fighters, U.S. designers focused relentlessly on engines, airframes, and altitude records, while the physical limits of the pilots themselves received far less attention. New aircraft prototypes demonstrated impressive capabilities on paper. Turbo-supercharged engines allowed sustained flight at extreme altitudes, and test pilots were sent higher than ever before in military aircraft. Performance charts showed success. But inside the cockpit, reality was far harsher. At 30,000 feet and above, oxygen was scarce, temperatures plunged well below freezing, and even simple tasks demanded intense effort. Pilots reported numb hands, blurred vision, and overwhelming fatigue. Oxygen masks were crude by modern standards, prone to leaks and freezing. Heated flight suits were experimental and unreliable. In many cockpits, insulation was minimal, allowing outside air to turn metal surfaces into ice. Engineers knew these problems existed, yet they were treated as temporary inconveniences rather than mission-critical threats. The culture of wartime urgency played a key role. Test pilots were expected to endure discomfort and danger as part of the job. Complaints were often downplayed, and reports emphasizing aircraft performance carried more weight than those describing human suffering. Success was measured in altitude gained and speed achieved, not in pilot endurance. Training manuals reflected this mindset. They emphasized procedures and mechanical systems, but offered limited guidance on prolonged exposure to extreme cold and hypoxia. The assumption was that discipline, toughness, and experience would compensate for biological limits. Few planners fully appreciated how quickly hypoxia could impair judgment or how cold could rob a pilot of the ability to move at all. As American aircraft pushed deeper into extreme altitudes, a critical weakness began to reveal itself. Not in engines or wings, but in heat. The heating systems and flight clothing meant to protect pilots from lethal cold were dangerously inadequate. What engineers had treated as a secondary concern was quickly becoming a life-threatening flaw. Most U.S. fighter cockpits of the early war years were not pressurized, and heating relied on ducting warm air from the engine or exhaust systems. At extreme altitudes, this heat often failed to reach the pilot effectively. Leaks, poor insulation, and frozen valves allowed sub-zero air to flood the cockpit. Temperatures could drop to -40 degrees Celsius, turning metal surfaces into ice within minutes. Flight clothing was equally problematic. Early heated suits depended on fragile electrical wiring that frequently malfunctioned. Gloves restricted movement, while boots offered little protection against frostbite. Pilots reported losing feeling in their fingers and toes so quickly that they could barely operate switches or trigger mechanisms. Once numbness set in, recovery was almost impossible at altitude. Engineering reports acknowledged these shortcomings, but fixes lagged behind operational demands. The priority remained altitude and performance, not pilot survival. In some cases, designers assumed that brief exposure times would limit risk. In reality, missions and test flights often lasted far longer than expected, trapping pilots in freezing conditions without adequate protection. Worse still, cold affected more than comfort. Oxygen systems froze, causing airflow interruptions. Condensation turned to ice inside masks, making breathing difficult. Instruments stiffened or failed entirely. What appeared to be isolated equipment problems were, in truth, symptoms of a systemic design oversight. The consequences were predictable and severe. Pilots suffered frostbite, hypothermia, and near loss of consciousness. The danger that engineers had warned about finally became real during a high-altitude test flight over the United States. The aircraft climbed steadily past 30,000 feet, its engine performing exactly as designed. Outside, the sky darkened and the temperature plunged. Inside the cockpit, however, something was quietly going wrong. The heating system, already strained by the thin air, failed to deliver enough warmth. Cold seeped in through seams and panels, frosting the canopy and turning exposed metal into ice. Within minutes, the pilot felt his gloves stiffen. His breath crystallized inside the oxygen mask. Every movement required effort, and every second made the cold worse. As the aircraft leveled off, numbness spread rapidly. Fingers lost sensation first, then strength. Simple tasks, adjusting the throttle, switching radio frequencies, checking instruments, became painfully slow. The pilot attempted to report the problem, but his voice weakened as condensation froze in the mask. The cockpit was no longer a workspace, it was a freezer. The most terrifying moment came when the pilot realized he could no longer move his hands with precision. Ice had formed around controls, and his muscles refused to respond properly. Training offered little guidance for such a scenario. There was no checklist for losing bodily control at altitude. The aircraft was still flying, but the human inside it was shutting down. Descent was the only option, yet even that required physical coordination the pilot was rapidly losing. With great effort, he managed to push the controls just enough to begin dropping altitude. The descent was uncontrolled and dangerous, but it was the only way to bring warmth back into the cockpit. As the aircraft fell into denser air, sensation slowly returned. Pain followed numbness, a brutal sign that frostbite had nearly taken hold. The pilot survived, but the flight ended in shock and silence. The data collected from the mission showed success. As the aircraft drifted lower from its frozen ceiling, the pilot's situation grew even more desperate. The descent had begun, but control was fragile, and his body was still struggling to recover from extreme cold and oxygen deprivation. At high altitude, survival was no longer a matter of flying skill. It was a race against time. Moments earlier, radio contact with the ground had faded into static. Ice had formed in the microphone, and the pilot's voice weakened as hypoxia dulled his awareness. Ground controllers heard only fragments before the signal vanished completely. To them, the aircraft became a moving, without a voice, descending without explanation. Inside the cockpit, the pilot fought to stay conscious. His vision narrowed, darkening at the edges. Each breath felt shallow, as if the air itself refused to cooperate. Training manuals warned about hypoxia, but experiencing it firsthand was terrifying. Judgment slowed. Seconds stretched unnaturally long. Simple decisions felt impossible. The aircraft responded sluggishly as the pilot struggled to coordinate frozen hands and fading concentration. He knew that losing consciousness would mean certain death. Without radio contact, there would be no guidance, no rescue instructions, only gravity and chance. Every movement was deliberate, driven by instinct rather than clarity. As altitude decreased, pain returned to his limbs, sharp and overwhelming. Blood began to flow back into frozen tissue, sending waves of agony through his hands and feet. Yet the pain was a sign of hope. Warmer air was reaching the cockpit. The aircraft shuddered, but it remained airborne. On the ground, controllers waited helplessly. Protocol offered little guidance for a pilot lost to cold and silence. Aircraft were built to report failures, but there was no system to warn when a human was failing instead. The sky concealed the struggle unfolding above. The incident did not remain a quiet entry in a flight log. Within hours, reports moved up the chain of command, stripped of technical optimism and filled with uncomfortable detail. A pilot had nearly died not because of enemy fire or mechanical failure, but because the aircraft had carried him into an environment he could not physically survive. For senior commanders, this was deeply unsettling. Briefings that followed were tense. Engineers presented altitude charts and engine performance figures, but attention quickly shifted to the human consequences. Medical officers described symptoms of severe hypothermia and hypoxia, warning that repeated exposure would almost certainly result in fatalities. What had been framed as an acceptable risk suddenly looked reckless. The timing made the situation even more alarming. The United States was preparing for expanded combat operations, and any new fighter program had to be reliable, repeatable, and safe enough for mass deployment. A design that pushed pilots to the edge of consciousness could not be justified, no matter how impressive its performance numbers appeared. Orders were issued with unusual speed. Test flights at extreme altitudes were suspended. Engineers were instructed to halt further development until heating, oxygen, and pilot protection systems could be re-evaluated. Some experimental aircraft were grounded entirely. Others were quietly reassigned or shelved, their data archived rather than celebrated. Behind closed doors, frustration ran deep. Years of work and millions of dollars had been invested in the high-altitude concept. Yet the incident had exposed a flaw too serious to ignore. The project had outrun its own safety assumptions. Commanders recognized that pushing forward without addressing the human factor would invite disaster. The decision sent a clear signal throughout the Army Air Forces. Performance alone was no longer enough. The suspension of the high-altitude project forced the U.S. Army Air Forces to confront an uncomfortable reality. The danger had not come from flawed engines or enemy action, but from the failure to fully account for the human being inside the machine. In the pursuit of technological superiority, the human factor had been treated as adjustable, when in fact it was the most fragile element of all. Wartime investigations revealed a pattern. Engineers had assumed that pilots could adapt to extreme environments with better discipline and marginal equipment improvements. Medical officers, however, presented evidence that contradicted this belief. Hypoxia impaired judgment long before a pilot realized it. Extreme cold reduced motor control to the point where even experienced airmen became physically helpless. These were not weaknesses of character, they were biological limits. The implications extended far beyond a single aircraft program. Military planners recognized that any system pushing technology faster than human capability created hidden failure points. A pilot who could not feel his hands could not fight, land, or communicate. An aircraft that flew higher than its crew could survive was, in practice, unusable. This realization reshaped design philosophy. Human endurance was no longer considered an afterthought. Cockpit ergonomics, thermal protection, oxygen reliability, and workload management gained new importance. The war had demonstrated that superior machinery meant little if it incapacitated its operator. Historical parallels reinforce the lesson. Early submarines, tanks, and artillery systems had suffered similar failures when crew safety was sacrificed for performance. Aviation simply made the consequences faster and more lethal. In the air, there was no margin for human collapse. The harrowing incidents of high-altitude flights during World War II left an indelible mark on aviation design, quietly influencing the next generation of aircraft. Engineers and military planners had learned a brutal lesson. No matter how advanced an aircraft's performance, it was meaningless if the human inside could not survive the environment it created. The failures of early American high-altitude fighters directly shaped the development of pressurized cockpits and more sophisticated environmental control systems in post-war jets. Designers of the first operational jet fighters, such as the F-86 Sabre and F-100 Super Sabre, carried the knowledge of frozen, incapacitated pilots into every technical decision. Cockpits were sealed and pressurized, ensuring that pilots could operate safely at altitudes previously considered unmanageable. Heating and cooling systems were integrated and tested rigorously, with redundancy built in to prevent the kind of near-fatal exposure experienced by early test pilots. Oxygen delivery systems were automated and more reliable, reducing the risk of hypoxia during rapid climbs and high-speed maneuvers. The influence extended beyond immediate safety improvements. Ergonomics became a core consideration, from control placement to visibility, allowing pilots to maintain situational awareness and react quickly under stress. Flight suits evolved alongside aircraft systems, incorporating insulation and compatibility with life support equipment. Every component was now measured not only for performance, but for human survivability. Military doctrine also evolved. The U.S. Air Force recognized that pushing pilots to the absolute edge of endurance was not a viable strategy, and training programs began to emphasize physiological limits as well as combat skills. Lessons from World War II were embedded in every new aircraft program, shaping requirements for altitude ceilings, environmental controls, and emergency procedures.